It's an honor to introduce today's speaker. I will keep my remarks brief. I met Professor Ottino when I was still a graduate student, and he was a visiting professor at Caltech. But to tell you his path, he was a student in Argentina. He came to the United States to do a PhD in chemical engineering at the University of Minnesota. After a faculty stop at UMass Amherst, he moved to Northwestern, where for many years he's been the Dean of Engineering. For those of you who know Julio, he brings to his work creativity, inspiration, and connections to fields far beyond things that you would have thought of, and he shows you how they're connected and reinforce one another. He's a member of the National Academy of Engineering and the National Academy of Sciences, and it's a real thrill to hear his upcoming talk for the G.I. Taylor Medal. Julio, the floor is yours.
Thank you, Howard. Okay, so thank you so much. I want to start by thanking the people who nominated me, the people who instigated the nomination, the people who supported the nomination, and the many people who came in the session about this award, the G.I. Taylor Award. Being honored with the G.I. Taylor Medal kind of offers an opportunity to look retrospectively to one's career, and it's almost an obligation when you get an award like this to talk about your work, especially recent work. But I also want to talk about G.I. Taylor, and I will talk about my work, but in order to connect the two pieces, I want to use something as a point of connection that I leave it undefined for a moment. It will become clear. So, but the talk will be basically three pieces. A little bit about G.I. Taylor, a little bit about me, and in between the connections. Now, most of us do many things, but in retrospective, we are always associated with one or two things. So my name has been associated with mixing, that's why it's in there. Now, I hope that at the end of the connection of these three pieces, me, G.I. Taylor, the connecting piece, there will be some lessons. Some lessons will be historical. Some lessons probably will be applicable to people who are starting careers now, because they have to do with the importance of timing, things like that. But in order to develop the talk, I'll make reference to creativity, multiple discoveries, and then what I call, well, breakthroughs. Everybody talks about that, but break with, okay? Now, in talking about what I have done, I probably will follow the admonition of Helmholtz in there, that he said that when one receives accolades, he was talking about Nobel Prize, okay? One tends to recount your career in terms of the royal path, in terms of, instead of the shaky ladder that actually brought you to that point. So what I'm going to avoid is talking about the royal path. I will talk a lot about the shaky ladder. You will see that some things you discover late, and it will have been so good to discover them early on, but I will mention those things. Now, let me start with G.I. Taylor. So in the bottom left, you have a paper that G.I. Taylor did when he was about 22. And the paper was communicated by J.J. Thomson, who won the Nobel Prize because he discovered the electron. And it was the only paper that G.I. Taylor did that was about what was going to become the new physics, quantum mechanics. And on the right, you have Niels Bohr, who became one of the creators of quantum mechanics, but the very first paper that he did was on fluid mechanics. And he also won an award for this paper. He was about 22 also. But they kind of went in opposite paths. So Taylor was born almost along the same time as Rutherford, Einstein, Bohr, Schrödinger. All of those people collected lots of glory because they became associated with the development of quantum mechanics, and it was good for them. And Taylor switched the other way around, stayed with classical physics, okay? So it was a good move on the part of Schrödinger and company, but it was also a good move on the part of Taylor, staying on the classical physics side. Now, when I started my PhD, I was supposed to work on trying to understand impingement mixing. Two jets collide in a chamber, mixing quickly, producing a reaction that led to polymerization. And in order to do that, I started thinking about pictures, and I drew pictures like the ones that you see there, a blob deforming. Eventually, if it's deformed enough and you cut a little cube out of there, you'll see a lamellary structure. And the idea was to look at reactions in between those lamellas, what you see at the bottom in there. And I really wanted to draw inspiration. And it became clear that I need to know some kinematics. So I started consulting books, and there were lots of books to consult about pictures. The one that came late for me was the Album of Fluid Motions by Van Dyck, but almost all the books there, from Lamb to Batchelor, Aris, the Handbuch der Physik by James Herring, they have an obligatory little one page on strict lines, path lines, and that's about it, okay? And I need to know more. I wanted to know more. So I was down the road in chemical engineering here in Minnesota. The department had its own library, and in the library, they had the 4 collected books of G.I. Taylor, the works. Volume 1, by the way, is about mechanics of those 4 books. And I couldn't get the original ones, nice leather bound, so I got this, and I spent a day or two looking at them. And I remember looking at pictures, and there were lots of pictures, some of them really complicated pictures of path lines, streamlines, what you see there. Some were sketches, like the bottom right in there. And it became clear that I need to know more about kinematics, and I was lucky. I was in Minnesota. There was a very nice group on continuum mechanics. I learned a lot of my kinematics from Roger Fosdick, and very quickly, things like what you see there became important, the stretching and things like that. Now in mechanics, you stretch things a little bit, not by a factor of 1,000, but I was interested in things that will stretch by 10 to the 4th, okay? And very soon I was drawing pictures like what you see there, how the things will stretch in a vortex, but also looking at reactions in between those lamellas. And in about 82, I was lucky enough, I was in the middle of the screen there, you see a paper in JFM about mixing in terms of the concept of material interfaces. So what I was looking in G.I. Taylor's work was if I could discover the glimpses of creativity, because I wanted some good creative idea. I wanted to see how someone had done it. So let me make a couple of comments about creativity, okay? This is an area that has preoccupied philosophers and many more. And if you look at Kant, he placed Newton's creativity below Homer because He, in my view, mistakenly thought that you could follow step by step what Newton had done, but you couldn't do that with Homer. In fact, one of the most creative things in humanity, in my view, is anything connected with math, okay? But let me kind of mention something more concrete. Herb Simon, a hero of mine, he won eventually the Nobel Prize in economics, but he contributed to so many things, okay? You see there. He listed 3 characteristics of creative people, and he knew lots of them. One was continuing preoccupation with a problem for long periods of time. The other one was willingness to accept imperfectly shaped ideas and shape them in the course of time. And then the one that is the usual 10,000 hour rule, okay? The extensive background in an area and related areas. The key thing is related areas. So for example, who would have thought that knowing something about computer science would have been really important in biology? But after sequencing, that became important, but no one knew it at the point. So Kant put creativity, artistic creativity on a high plane, so let me kind of say a word about this. So in here you have Malevich, who was a Russian constructivist, a painter, and this is how Malevich started. This was some of the original paintings that he did, and then he evolved like that, and then he went up to here, and if you think you're done, no, he ended up with that, okay? So the point that I'm trying to make is you can see the evolution in Malevich, and if I show you this picture and I ask you how it was that came about, you will have no clue. But art leaves a trail. In math, you don't leave a trail because all the things, the scaffold that gave rise to the idea, you leave it because you want to have something perfect out there for everybody to see. So this is another example that I mention often. This is a series of lithographs by Picasso. When I show this, people think that the bottom right, the few lines sketch, is the first, and the full bull on the top left is the final one. But in fact, he did the reverse order. He went from complex to simple. And this is an idea that is also important. The ability to go from complex to simple, that comes about when you extract the essential components of a problem. But then once you have the core part of the problem, how you go from that idea and you bifurcate into other ideas. Now, I alluded a little bit to images and J.I. Taylor, so some people have thought more about this than I have, and Gerald Holton in Harvard wrote a very nice article about the visual imagination of famous scientists. On the non-visual side, he put Heisenberg, Lagrange. Many of you in the audience probably will know that in the book Analytical Mechanics, in the preface, he said, "You shall find no images in this book." Okay, that was a point of pride and Weierstrass. But the visual side is as illustrious as well. You have Riemann, Hilbert, there were lots of pictures in Hilbert, Feynman, and even Einstein. So what pictures did you find in J.I. Taylor? So these are all coming from the mechanic side. And as soon as you see these pictures, you have to see an active imagination on the visual side. And then you find images like this. This is more rare. This is a little bit like the codices by Da Vinci. Da Vinci didn't number the figures, figure 1, figure 2. He was writing, and at some point became clear that he needed some argument, drew the picture, he continued. So J.I. Taylor has a few like this. This is a figure with no caption, no number, nothing. But then there are a couple of images in some papers that as soon as you see the image, this has to do with a paper on dispersion in tubes. As soon as you see the image, especially the one on the right, you almost see how the idea has to follow, okay? And he did it, and the paper is kind of hard to follow. In the same way that, for example, if you read the Einstein paper on diffusion, it's pretty arm-waving, the paper, but the ideas are there. And then someone comes and produces a much better, more refined version. And in this case, Gus Aris, who was in Minnesota, produced a beautiful, more complete version of the ideas of the Taylor diffusion, and now it's called Taylor-Aris diffusion, with absolutely not a single figure in the paper, okay? So the other concept that I want to allude is the concept of multiple discoveries, and that has to do with the idea of the adjacent possible. I mean, this meeting is a good example of the adjacent possible. We are all here, we are all at the frontiers of a domain or several domains, and maybe two of you will connect and produce an idea that is new and advances things a little bit, an epsilon more in there. So some people have studied this in detail, and a fellow named Robert Merton studied this with Kelvin, Lord Kelvin. And of out of 400 scientific communications, there were about 32 that were communicated almost at the same time that Kelvin communicated them. But if you look at the names of the people who communicated the ideas at the same time as Taylor, it's a very illustrious group. It's Stokes, Green, Helmholtz, Cavendish, and then second order, we like to be in the second order, like Hankel and Lamé and people like that. So this does not diminish Kelvin's greatness. What this says is that in order to match some of the things that Kelvin came across, you needed this other set of people to validate the ideas, okay? Now, Taylor's name is associated with lots of things, okay? Lots of, he's not known for one thing, he's known for many, many things. And the question is, how many of these will be anything in the area of a multiple discovery, and how many of them would be what I would call breakthroughs and also break-with? So a breakthrough, in my view, is something that breaks through the domain and enlarges the domain, and the domain becomes richer because of that thing. A break-with is something that is so radically different from everything that generated things in the domain that is outside the domain, and then you have to call the domain, for example, you have classical physics, and then you have quantum mechanics and relativity, and you will call the whole thing physics again. But that was a break-with, okay? So let me do the connection between Taylor and the rest with something that is a break-with, and is the issue of determinism. Determinism comes from Laplace. He imagined an all-powerful being that if you knew the initial conditions of everything, momentum, you could basically predict the future, okay? In fact, even Newton had reservations about the idea. What you see at the bottom paragraph in there, unless I'm much mistaken, it will exceed the force of human wit to consider all the causes to produce something that will advance the clock in time. But the point is that determinism was so embedded as the frontier in physics that at some point people decided that they needed a jolt to move from the solution from the two-body problem to the three-body problem. Now, the two-body problem, Earth, Moon, or Earth, Sun, has given rise to lots of discoveries, but at some point it was known that the orbit of Uranus was not behaving as it should have been. There were deviations of 30 seconds. The calculations were enormously long, but people were unsatisfied. There is a whole even book about this. Jane Bauer Green wrote about the three-body problem. But there was a prize established for the first person who could produce this a solution to the three-body problem. Okay? Mittag Leffler convinced the editor of the Acta Mathematica from Sweden to give big prize, well, actually the king of Sweden, to anybody who could solve this first. And why this? Because the faith in determinism was so enormous. In fact, Neptune was discovered by bad calculations. As I mentioned, Uranus was not behaving the way that it should have been, and there were lots of reasons why they thought this. They never thought that Newtonian mechanics would have been wrong. There had to be another force out there, and someone postulated the existence of an unknown planet, and two people worked simultaneously, Leverrier and John Couch Adams. They announced, Leverrier in France kind of announced this first, and said, if you point a telescope in such and such a direction, you will see this new planet coming into being. And lo and behold, what now we call Neptune appeared. So that's why people were so invested in having the solutions to the three-body problem. Eventually, the one who won the prize, and there's a whole bunch of related stories about this, because the prize was published, they discovered a mistake, Poincaré had to buy all the issues of the journal. Fortunately, he was very wealthy, and they gave the prize to him, but no one thought that the prize was of any consequence. Now, Poincaré discovered in producing the solution that there was something really unwieldy in what he had found. And he has this phrase, which is famous, that I'm not going to attempt to even draw what I discovered, okay? But basically, what he discovered was what is called homoclinic and heteroclinic intersections, which is a fingerprint of chaos. Now, at the same time that this was going on, Osborne Reynolds, famous now because of the Reynolds number, gave a little talk at the Royal Institution, 2 pages long, no references, no figures, in which he talked about basically the essence of mixing. But the main reason that I'm mentioning this, there are 2 reasons that this is perfect for this connection. One is that Reynolds thought that in terms of the mental effort trying to uncover motions of fluids, this was enormously complicated, so he compared that with the biggest problem that he could think at that time, and he said it's probably more important in terms of time and effort than the discovery of Neptune. That's one reason. But the other reason is that Reynolds came up with an idea about mixing that had to do with stretching and folding, okay? And these 2 people, the third reason that they are together, they died months apart, the same year, months apart. The obituary about Reynolds is sort of standard. He was well known, but the one of Poincaré, the English were gushing about Reynolds, and they even said the world has lost by the death of Henry Poincaré, one of the greatest men who have lived in the present century, and they even praised him for the command of the French language, which was super unusual coming from the English in there. But Poincaré was a member of the Academy of Letters also, okay? But they also mention as that he did not succeed in solving the three-body problem, should not be constitute a failure, he tried, that kind of thing, and left him there, okay? And then With Reynolds, something that they mention is that, which I will go up to the end, is difficult at the present time to estimate the place which his last great work, The Sub-Mechanics of the Universe, will take. We will need he had been right before, so we will wait, but that was the last thing that Reynolds did. So this is probably the most important slide. This is when they were born. In here you see when the three-body problem is announced, when the solution of the three-body problem appeared. At the same time, Reynolds comes with his little paper on stretching and folding. And then, as far as I know, they never met. Poincaré was going to be at the Congress, the World Congress of Mathematics in Cambridge, but he had been sick in the previous Congress, which was in Rome, and he couldn't attend. Reynolds, actually, his first degree was from Cambridge, could have been met in there. And one amazing thing is that if you look in there, when they died and when the obituaries were published, I have no idea how this could happen. Within 3 weeks of them dying, the obituaries in Nature appear for both of them, okay? So, as to the timeline, not a royal path, I recently moved offices, I vacated the dean's office, I found lots of papers, and I found that I was doing things like trying to find out could the strict lines cross on themselves. The answer is yes. But very early I was drawing pictures like this, stretching and folding, without knowing really that Reynolds had published that little paper, okay? And with the stretching and folding, at some point it became clear that in systems that you could perturb from some ground state, you could have these manifolds that will pile up along hyperbolic points, and these were these manifolds that Poincaré had mentioned I couldn't draw. So in here, for example, in this picture, you have somewhere in the middle of the picture a hyperbolic point, and then this pile up of folded striations that are the manifolds that Poincaré was talking about. In here, in another picture, you see the same thing at the middle, the top, and they are the same piling up. So, and the reason that all of these things were happening is because we have discovered that in order to produce chaos, you have to find a way of building what is called a horseshoe. Okay? It's a piece of material, mathematically, that comes folded upon itself. And by the time that we wrote this paper, the word horseshoe, I think, appeared like 14 times in the paper. And horseshoes, we started drawing them, things like that. And then once you have this, you could do lots of things like, for example, place little blobs in fluid flows, knowing that one of them, if you are careful, will not do much, and the other one will do lots of things. Now, in here, you see the green one is kind of, it's a mild stretch, the other one is a stretch and folding a lot. And we got away with publishing this appear in Nature. If the picture had been taken exactly at the right time, the picture will be completely symmetric about the mid-axis, okay? But it was too complicated to do the things and identify the points, so we were let go with that. So the point is that only subsequently we discovered that the word mixing in a completely different context appears in math, but translating this back to physical system is that if you have a blob and a test area, you want part of the blob to appear in the test area, no matter where you put the test area. And so you want the intersection of the map blob and the test area to be non-zero no matter where you put those things. And depending on how strict you are, you have different definitions of mixing. One of them, the one that I mentioned in passing, was the horseshoe, which is stretch something and fold it. And then the other one, which leads to even better mixing, is the one in which you actually stretch but then cut. And so far cutting, given the fact that we started with continuum mechanics and flows, cutting was not allowed, but this leads to another more strict definition of mixing. And you can have, for example, in the intersection of an infinite number of, a countable number, but infinite hyperbolic points in this set of intersections of forward and backward motions. In fact, this, I'm not going to go through this, but this is probably one of the only practical demonstrations of binary numbers that I have ever seen, because the Baker's transformation, which is the stretching, cutting, and stretching, cutting again, is basically moving binary digits to the right and then inserting the one that you left on the left of the other coordinate. And right off the bat, you almost see that if you have any initial condition, xy, which is a ratio of two numbers, no matter what the numbers are, is going to be periodic, and you're going to have periodic points of any order that you want in here. Now, what we also did not know initially is that if you have a domain, let's say a cup of coffee, okay, and you stir it, and you let the motion die, there is one point that before and after is going to be in exactly the same location. That's a Brouwer's fixed point theorem. It's about 1910 or something like that. So if you have a periodic motion and you have two states, there will be one point that has not moved. And then if you have a composition of two more, there will be another one, and so on and so forth. And you can see this here, for example. This is an evolution of a picture of mixing. You have this yellow dot that moves there, move there, move there, there. And once you have it for 2D, you can have it for 3D. In this, the cut will be the 2D equivalent. And when you look at pictures like this, you have islands will be tubes, and the coexistence of the tubes with the chaotic regions in there. And of course, 3D examples like what you see here, which is a textbook case of what, there are several theorems that apply for systems that are not that perturbed from the integrable case, okay? And the Camp theorem is one of them. The picture on the lower right is what Camp theorem will tell you, and it's almost a textbook example of what you see there in the experiments. So the broader landscape for me is when we work in mixing, we thought this was the landscape. We mix the microfluidics. We work on many other things, droplets, aggregation, fragmentation, autocatalytic reactions. There were a whole bunch of things. And then we went into granular materials. And the first thing in granular materials that we did should have been this, because it's the closest thing that you have to a continuum description. But instead, we work on things that were geometric like this, mixing by avalanches, and this was fine. It was purely geometric. This was our strength. And then we could have gone into other things like issues from macro, micro, macro transitions, axial, but instead we went in one direction that is something that Reynolds worked on. Reynolds was fascinated by granular matter. That's why the picture is there with containing some granular material. And the issue that has to do with Reynolds and dilation is that when a granular material flows, it expands, and smaller particles can fall through. The same thing happens with density differences. And when you look at things that are initially mixed, they can unmix and produce patterns like what you see there, okay? In this case, the variation is due to geometry because the layer becomes longer and shorter, or because you force the layer in a time periodic fashion. So with this, and there are people who know more about this than I do, you can construct convective diffusion equations where you can incorporate the segregation term, and you can come up with pretty good descriptions involving a comparison between analytical models, computations, experiments, but also direct simulations in terms of particle discrete element methods. So, but you don't be surprised that one of the areas that you move on was, we were very much into time periodic flows, was time periodic flows in an sphere. And what you see there is an sphere, but in the super idealized case in which the layer becomes infinitely thin, the issue becomes like what you see here. Let me see if I can work. No, it doesn't work here. This always happens with movies. So what will happen in here, if I can make this, I'll have another chance, is that in here we are moving in a situation in which before we forbade this to occur, which is one particle breaking into two, because there are cuts. And what the question is, what happens if we allow this to happen? And what happens is that you have something that moves in relatively new area of math, which is piecewise isometries. Piecewise isometries involves having domains, cutting them, reshuffling them again, cutting and restarting the same transformation, and you are going to see a whole bunch of cuts that is what is called the exceptional set. And then you see parts that, like in the fluid mixing, that they do not mix at all, islands. And in here you see another one again, a little bit more. But you see that the area that doesn't mix rotates a little bit. So when you look at so in here you'll see domains. In here, a whole issue that flew for some angle is now moved by the other axis, and this is repeated. And when you do that, this is looking at a container filled half and half. You get things like this. And up to this point, the bottom one is less mixed than the upper one, but then when you keep going, the upper one is like that. And this moves you into an area that creates these fractal-like structures of the exceptional set. And these fractal-like structures actually have the same dimension of embedded space. Why they do that, I have no idea, and I asked people who were supposed to know this, in fact, the people who invented the word fractal that goes with this, and no idea either, okay? So this is something that was so idealized, and instead it has this layer of complexity in there, okay? You can do experiments, you can track laboriously particle with maybe X-rays, and you can see how they map into these very clean models. And let me just go back in here to Reynolds. And the issue of creative longevity. So Reynolds started producing papers at 22. The last paper was at 85, okay? Whereas Maxwell, for example, which by the way I put this quote that advising people to read the papers of the original authors to get an understanding of how they did what they did. Maxwell, for example, is famous for kinetic theory, statistical mechanics, electrodynamics, but he wrote a whole bunch of papers on structural mechanics. In fact, there is a book coming from Cambridge University Press on the paper of Maxwell on mechanics, which is much longer section of what he did than the other part. But Maxwell is one of the people who peak early. By the time he was 40, he was done. He had a long life, but there are people in many domains who, Frank Lloyd Wright built more than half of his buildings after he was 60. Louis Bourgeois, if you ever are at the Guggenheim in Picasso, she has a sculpture there. She was doing work at 95, okay? Picasso peaked early, Cézanne late. More than 60% of what is reported in books about Cézanne's work is when he was more than 60. But when you look at people in science, you have this category of innovators and experimenters, or young geniuses and old masters. Maxwell, Stokes, Einstein, best work when young. Lord Rayleigh won the Nobel Prize at 62, which in those days was old, okay? And produced steadily for 50 years. And G.I. Taylor, as I said, first paper 22, 23, and the last paper, he couldn't attend, the World Congress of Mechanics was published at 87. Now, how about Reynolds? Reynolds produced this final work. He had to publish it himself. But he received accolades. And one accolade that he received was giving this ready lecture in Cambridge in 1902. Remember, 1905 is the critical year for physics. It's when quantum and relativity explode. And J.J. Thomson, the one who was the sort of advisor of G.I. Taylor at the beginning, had done the lecture in 1986. My sense is that Thomson recommended Reynolds for this lecture, because Reynolds actually was the one who recommended Thomson for admittance in Cambridge, okay? But in this lecture, the ready lecture by Rayleigh, he talked about the submechanics of the universe, okay? And the first sentence, I don't know of any sentence in any paper anywhere that is more gutsy than this, okay? Is by this research, it is shown that there is one and only one conceivably purely mechanical system capable of accounting for all the physical evidence as we know it in the universe. And he said, here it is. And no one understands this paper, okay? But it's basically a theory of the ether. The obituary, or the analysis of the paper, basically says if Professor Reynolds does in this what he promises in his resume, he will go down to posterity to a greater fame than Newton, okay? Obviously that didn't happen. So let's go back to G.I. Taylor. So Herb Simon said continual preoccupation for problems over long periods of time. I don't know what problem preoccupied Taylor for a long period. Turbulence was one, okay? Willingness to accept vaguely defined problem statements, fine. And extensive background knowledge. Taylor, in fact, his education was almost self-made, never got a PhD really. But in multiple discoveries, The only one that he had was a motion of dislocations with people like Polanyi at the same time. This is basically what I was told. But was he a young genius or an experimenter? And the answer is kind of both, okay? Is also an exception to the rule of being remembered for one thing. He also was lucky with the timing. Schrödinger and all the other people move in one direction, and Taylor stayed there and collected the benefits from staying there and having this absolutely clear thinking. He was also early in infusing fluids with more math. In fact, the term applied math did not appear until those world conferences that mentioned that Poincaré was attending. It was not there, okay? And benefited from having, it's an amazing collaboration. He had the same assistant, no secretary, for all his career, okay? As to any lesson coming from my side, I think you have to get lucky with what you pick, but I would say that I'm one of the beneficiaries of having extracted some concepts from pure math. So thank you for your attention, and I would like you to know how appreciative I am that you took the time to be here today. Thank you so much.
Julio, thank you for an amazing talk spanning from creativity to science to art. I'm not sure how much time we have.
I'm not keeping the time.
Well, let's assume we have time for questions. So are there questions from the audience?
I usually get this reaction.
Well, so maybe I'll just ask one. When you then think about Reynolds and Taylor, and at least one area on your map of Reynolds that you didn't include, I'm wondering if you think it's relevant or not, is lubrication theory.
Yeah.
Which is not often mentioned in books, but is a very useful idea.
Yeah.
But maybe it stands separate from turbulence and others. But
No, that Reynolds was more of an engineer. He has a fascinating story. He had no lab. For a long while, he had a whole area that he called outdoor physics, because he would basically go out and look at things and try to come up with ideas. No, lubrication was recognized. And the thing that was forever associated with him was the idea of having emotion with fluctuations. That came after the first paper with the criterion of the transition to turbulence. So those things were recognized, and they are mentioned in obituaries. Except that at the end, he came with this grandiose idea that didn't go anywhere. I mean, but that paper, by the way, the submechanics of the universe, is what the Reynolds transport theorem appeared.
really?
Yeah, it's in there. Yeah.
So the paper's not completely.
No.
Anyone want to add? Jim.
So you talk about these breakthroughs, right, in innovation. You talk about breakthroughs in innovation, kind of this setting of stages, right? And noticing this conference, there are many places where you could see maybe traditional extrusion became 3D printing, right? Origami 30 years ago was a game you played with paper, right? And now it's like, how many sessions we had on origami it's amazing, right? How do you foster an environment that's going to do this, right? To innovate beyond what we see as commonplace into the next thing?
everybody in your own respective department, university is trying to do that in some way. And that's why you have meetings, is to encounter people. You will connect with people who are doing something similar to what you are doing, but occasionally you will have the unexpected connection of someone who is doing something that you never thought about this before, and then you put two and two together and you do something. I should say something about Taylor, because I wouldn't say that anything that Taylor did was a breakthrough. Something is a breakthrough when people know what the problem is and they're expecting someone to solve it. But he basically, when they're collecting problems, solving them, and then moving on. And in that respect, I know no one else like that. He will pick one thing and be done. With the dispersion in tubes, he did maybe 3 papers, and then created an industry of people who are doing that. And there are things like Rich Lepto there knows how many papers have been done about the wet Taylor instability and all of those things. So the idea of how do you create a creative organization. Recently I wrote a book and I get into some examples of this. From the Bauhaus to Bell Labs to Black Mountain College. Black Mountain College, probably no one knows it here. If someone knows about Black Mountain College, raise your hand. Okay? But Black Mountain College was the first place that Buckminster Fuller showed a geodesic dome. And he was also the one with integrity and all of those things. But they were mostly artists, which is a good thing of art migrating more into science. But the idea of how do you create environment for collaborations, the things that I would have to say are reduce barriers, have a lot of tolerance for people who are at the fringes in there. We saw a nice example this week with the Nobel Prize of medicine. So there's no clear recipe. Everybody is trying to foster creativity and innovation in organizations, but there is no one method that solves all.
Okay, maybe we'll do this. We'll bring the session to a close. I just want to make a remark and then we can thank Julio again. I think what you've seen today is a remarkable example of science linking with creativity, and it reminds me of a quote of Louis Pasteur, chance favors the prepared mind. And I think that's how I often think about you, Julio, as someone who can integrate using as you would say in your dean's life, the whole brain, the left and the right brain. So thank you again for a beautiful talk.
Thank you.